Okay, section 5.2b begins and ends on page 246. Explanation for it. However, for you to understand some things, I need to show you two things that you have to be able to deal with here in order to make this work. So I'm going to step away from that for just a second and show you a couple of interesting things that happen in algebra, and then we're going to make use of them to simplify some radicals. First of all, can anybody tell me what they believe 2 root 5 times 8 root 5 is, without using your calculator?
16 root 5.
16 root 5. Oh. Nice try, but not correct.
86.
What do you think?
Oh, 8. 18.
80.
80.
Let me build on what you said just a second ago. You said 16 root 5, and it's not. It's 16 root 25. Because when you multiply radicals, you multiply things on the outside together, that's your 16, and you multiply things on the inside together to keep them inside, for at least for a moment. But we all know what this is. What is it? 5. So this is really 16 times 5. Yeah? So that's where the 80 comes from. So let me back up just a little bit. Can anybody tell me what they think this is? This is an easier problem. What's the square root of 3 times the square root of 3? 3. Right? What's the square root of 7 times the square root of 7? 7. Because you're really squaring root 7, and they are opposite, they're inverse operations, right? What do you suppose root x times root x is? X. What do you suppose root 5 times root 5 is? 5. So you don't have to have this step right here. It's going to be 16 times 5. Can you see that? Okay. So with that in mind, now I want to show you another one. I'll bring the two together and show you how it's going to help you in just a second here. Go to a different part of algebra that you've learned and do this with me. If you have x minus 3 times x plus 3. First of all, before we begin, I want you to recognize these are binomials because there's two terms each. That's what the bi is. You with me? These are binomials. Not only that, they are a conjugate pair because they look exactly alike. They both lead with an x, they both end with a 3, but the sign in the middle is different. And when you multiply a binomial by its conjugate, something cool always happens. The middle term adds out. Look, take x times x is x squared. X times 3 is 3x. Negative 3 times x is negative 3x. And negative 3 times 3 is negative 9. And these always add out. When you multiply conjugate pairs, you end up with x squared minus 9. You agree? So what would you get if you multiplied these two? If I multiplied 2x minus 5 times 2x plus 5, without going through the whole process, can you tell me what the end result would be on this? 4x squared minus 25. We call that a difference of two squares, and we know it factors into conjugate pairs. We learned that last trimester, right? But if you have a conjugate pair and you multiply it out, there is no middle term. We have an x squared term, we have a constant, but there's no x term because the difference in signs makes the middle terms add out, right? So let's see if you can carry that a little bit further. See if you can tell me, now that this is bringing both of those ideas home that I started with, can you tell me what, for example, x plus 2 root 5 times x minus 2 root 5 would be? X squared minus 20. This is what I'm asking you to remember. I kind of do the arithmetic in your head. When we multiply this times this, I think you all recognize that that's the thing you have to do, and it's negative. But it's 2 times 2 is 4 times 5. See it? Gives you the 20. Okay, so getting a little closer to what we're going to do with it today. Let's try this one. See if you can figure this one out. What is 2 plus root 5 times 2 minus root 5? Now we don't have any numbers. I'm sorry, we don't have any x's now. So what's it going to be? There's an intermediate step you can tell me about. What do you believe this is going to be? 4 minus 5, which is -1. Started out with things involving radicals, ended up with things not involving radicals. That's the key today. Let me try another one. What do you get when you have 4 minus 2 root 3 and 4 plus 2 root 3?
16.
Intermediate step is 16 minus
12.
12. Good, you guys are getting good at this. What does this actually turn out to be? 4. Nice and rational. No radicals. Let's try another one. See if I got, I got space over here. What would root 5 plus root 11 and root 5 minus root 11? What would that be? 5 minus 11, which is -6. Nice and rational. No radical symbols. Let's do one more. Let's take 2 root 7 minus 3 root 5. This will be a lot of arithmetic for you. And 2 root 7 plus 3 root 5. Tell me what you get for that.
14.
14?
Oh, no, it's 28.
I think it's 28.
Yeah.
Do you agree it's 28? Did y'all make that leap?
Minus, 45.
9 times 5, 45. Now, this is a little bit harder to do the arithmetic. What do you get when you subtract those? Anybody know?
17.
-17. -17. What I want you to notice is the bottom of every single one of these has no radical on it. This was complex. This was ugly. And we found a way to turn it into something that wasn't really pretty, but no radicals. We're going to use this method today, using conjugates, to rationalize denominators that have radicals in them that are binomials. Like this. This is what I mean. We're going to use this idea of a conjugate and how it really nicely cleans up the radical problem. And it's only going to be with square roots. We're not going to do it with cube roots and fourth roots and stuff like that. That's a whole other thing. We're not going to do it in this book. We're only going to try to rationalize, make denominators rational that involve binomials and square roots like this. If I have the fraction 1 over 5 plus root 3, it is not allowed to leave it in this form. You will miss it. It's wrong. It's not complete. It's not proper. So to make this thing in the denominator be something without a radical symbol, because it's a binomial here, we're going to use its conjugate to clean it up. Make good sense?
Yeah.
Because conjugates, when you multiply them, always end, well, if conjugate, radical conjugate, radical binomials conjugates, when you multiply them, always end up with something without a radical. So I'm going to multiply top and bottom by 5 over 5 minus root 3. Again, my objective is to multiply by 1, so it doesn't change the value of this, just properizes it. You with me? So that's why I chose the conjugate. Got to multiply the top by that as well. Happily on this one, it's not a very difficult thing to do in the numerator. It's going to be 5 minus root 3. The denominator is going to be, let's do a little sideline here. The denominator is going to be 25 minus
3.
minus 3. Yeah. Rationalize the denominator. This thing right here has exactly the same value as this, but this is proper. That's your goal today, is to rationalize denominators that have radicals in them that are also binomials by using a conjugate idea. Okay, let's try another one. Oh, I have 2 concepts to teach you today. Sorry about that. This will be one of them. The other one will go a little quicker. Let's take a look at. I'll just make one up. We'll just do one. I'll give you one that's really about the hardest you're going to encounter, and see if you can handle it. If so, we'll leave this concept. I have 2 minus root 7 over 3 plus root 5. That's about as ugly as it's going to get. This is improper because of the root 5 in the denominator. And it's being combined with another thing, so it's a binomial. What should we multiply top and bottom by? 3 minus root 5. The decision is made here. 3 minus root 5 on the top as well. So on the bottom, we probably know or can guess what we're going to get. We're going to get
9 minus 5.
9 minus 5. Big fat 4. That's what we want. Now we got to deal with the numerator, which means we're going to have to remember how to FOIL these out, and they are not a conjugate pair. It just requires FOILing, which means it's gonna have a radical. Here we go, here's what happens. Take the 2 times the 3, take 2 times negative root 5, that's negative 2 root 5. That's out, that's in, so they just stay separate. Negative root 7 times 3 is negative 7 root 3. Are you with me? I'm sorry, 3 root 7. Got a little dyslexic there. This times this is negative, there's my negative 3 root 7. And this times this will be a positive because it's negative times a negative. Positive what?
35.
Root 35. And then you take a look at these and you ask, are any of those combinable? What I mean by combinable is, could I add root 5 to root 7? No. Can you add root 7 or root 5 to root 35? No. And you might think, well, why not? Because, and that's the next concept. I should have presented that one first. But the next concept is, when you are combining, do y'all know what the word combine means in algebra? It means to add or subtract. It's a word which combines both ideas in one thing. And that's what we would be here. This step here would be a combining step. And you cannot combine radicals that are not alike any more than you can combine 3x plus 3y. You cannot combine those. They are not alike. This is not like this. So these are not like terms. Even though they're made up of numbers, they are not alike. Does that make sense to you? So there are no like terms up here. So at this stage, this one's done. But if there were like terms, you would be expected to combine those together before reporting your final answer. But when it comes down to the combining step, that's the whole next concept. When you combine, you have to have the same radicals behind these numbers. And if you did, like for example, if you had 2 root 7 minus 8 root 7, those are both root 7s. So you take 2 minus 8, just like 2x minus 8x, that will give you negative 6 root 7. That's the notion behind combining. When you get to the combining step, we're adding and subtracting, these radicals have to be the same in order to combine them like x's. So we have 2 of these minus 8 of these is negative 6 of these. It's a combination thing, okay? All right, so if you had no trouble with this and you recognize none of these are combinable, this would be how you would report your answer, then you're all set for this concept. And the last one is going to be, the last thing I need you to know is going to be shorter. I think you all understand. I'm going to try it with you one more time. If I have 3 root 2 minus 6 root 7 plus 4 root 3 minus 8 root 2 plus 8 root 7, can you tell me what that would combine to be if that was what you're doing? How do you simplify that? Negative 5 root 2, I heard. Does everybody understand that? What's going on? Okay. And then? Plus 4 root 3. There's only one of those guys.
Plus 2 root 7.
And that would be it, right?
Yeah.
Because the 2 and the 3 and the 7 are not alike in those radicals. So that's the best you could get on simplifying this one. So you understand that pretty well, combining like terms. This is where you can get the throws kind of a hitch in things if you know what you're doing here. I guess I'll write one in a slightly different way. What if I had 2 times 8 to the 1/5 minus 4 times 8 to the 1/5? What would you get there? Negative 2 times 8 to the 1/5. Because this is a radical, right? It's the 5th root of 8. That's the 5th root of 8. And I have 2 of these 5th root of 8 thingies minus 4 of these 5th root of 8 thingies. Now I have negative 2 of these 5th root of 8 thingies. It's the same notion. These are radicals. They're just not written with a radical symbol. And so if they're alike, you can combine them. So if they're written in a different form, still it's a collecting of like terms. Okay, one more thing. If I have the cube root of 54 minus the cube root of 2. At first glance, looks like you can't combine those because 54 is not like 2. However, while this one can't be simplified, there's no groups of 3 in there, this one might. That's the thing you got to deal with. At first glance, these are not combinable. Everything that I've showed you so far had prime numbers under here. Nothing, no pairs come out of prime numbers. So we didn't have that to deal with, but now we might. So we got to take that 54 and see if we can simplify that cube root of it. Anybody think of 2 things that multiply to be 54?
9, 6, and 9.
2 and 27, 6 and 9. I'm hearing 6 and 9 more often, but 2 and 27 would work fine. 6 and 9. This is 2 and 3, and this is, oh look, we got a triple, and that's what we were asked to look for. So one of these 3s gets to come out, right? This is 27. And that 2 times 27 was a good move, because if you recognize 27 as a cube, you don't have to go down to here. But it all works out. So these 3's right here, which are 27, cube root as a 3. So what I really have, and that 2 didn't come out, so he's got to stay in. I really have 3 cube roots of 2 here, minus the cube root of 2. Now they're combinable. And what's the answer?
2
cube roots of 2, because 3 of them minus 1 of them is 2 of them. You see it? So while at first glance it didn't look like they were combinable, not all of them were as simple as possible. So you got to get them as simple as you can and see if it works out so that they are like terms, and they are. We have 3 of these minus 1. Do you understand that? See what's going on? So you have to simplify every single term and then combine the ones that are alike. That's it. So you're going to be rationalizing denominators that are binomials, and you're going to be combining, possibly having both of those in the same problem. Combining those things that are alike, but you can't determine if they're alike until you simplify them as much as possible. Yes?
Well, I was just, I don't know, miss or something, but why is it a 2 instead of 3? But if it's from that last.
Here,
Yeah.
because this, remember in algebra, this is understood to be a 1 if there's not 1 there.
Oh, yeah, okay.
3 minus 1's 2. Yeah. Okay. All right.
Because it's just like.
Good question. Okay, for those of you doing it on paper, 19 problems today, and you got scads of time. You ever heard that? Your parents ever use that word, scads?
I've never heard scared.
Really?
Yeah.
My grandpa used it all the time, so I don't know if people who heard of it. Scads means a lot. So you got scads of time. Okay. All right. It is 29 to 47, all of them, but it's still only 19 problems. Okay? So get after it. Let me know if I can help you, and you should easily finish before you leave today. That's it. Bye.